In 1924, Satyendranath Bose at Dhaka University derived Planck's radiation law independent of classical electrodynamics on the basis of a new method of counting now known as Bose-Einstein statistics. Bose's scheme implicitly assumed that photons were not just identical but also indistinguishable. But this key assumption was stated explicitly only by Einstein in 1925. Bose's paper was rejected by the Philosophical Magazine, so he then forwarded the manuscript to Einstein, who recognized its importance, translated it into German, and sent it for publication to the Zeitschrift für Physik with his recommendation. Now, if two particles are indistinguishable, the probability of finding particle 1 at position R1 and particle 2 at position R2 is equal to the probability of finding particle 2 at position R1 and particle 1 at position R2. Therefore, since the probability is the square of the wave function, we can write psi of particle 1 at R1 and particle 2 at R2 modulo squared is equal to psi of particle 2 at R1 and particle 1 at R2 modulo squared. In 1926, Paul Adrien Maurice Dirac showed that this can be realized in either of two different ways. For bosons, we have psi of particle 1 at R1 and particle 2 at R2 is equal to psi for particle 2 at R1 and particle 1 at R2. Whereas for fermions, we have psi for particle 1 at R1 and particle 2 at R2 is equal to minus psi for particle 2 at R1 and particle 1 at R2. Both of these satisfy the first equation. The boson wave functions are thus symmetric to interchange of particle labels. If we switch 1 with 2, then we get the left hand side becomes equal to the right hand side. Whereas fermion wave functions are antisymmetric to interchange of particle labels. If we switch 1 with 2, then the wave function changes sign. For a fermion, such as an electron, if we put R1 equal to R2, the antisymmetry of the wave function requires that psi for electron 1 at R1 and electron 2 at R1 is equal to minus psi for electron 2 at R1 and electron 1 at R1. That is, the wave function is its own negative, which can only be true if the wave function is 0. Thus, the antisymmetry requirement makes the wave function go to 0 if two electrons are forced to occupy the same position or the same coordinates or the same set of quantum numbers. Thus, the probability of two electrons having the same set of quantum numbers is 0, and this is Pauli's exclusion principle proposed by Wolfgang Pauli in 1925. The statement of Pauli's exclusion principle is that there never exist two or more equivalent electrons in an atom which in strong fields agree in all quantum numbers. If there exists in an atom an electron for which these quantum numbers in the external field have definite values, this state is occupied. In conclusion of his article in Zeitschrift für Physik 1925, Pauli expressed the hope that at some future date a more profound understanding of the fundamental principles of quantum mechanics would enable us to put the exclusion principle on a firmer foundation, but for the time being he admitted that no deeper motivation for the rule can be provided. It was thus an empirical rule. We see, however, that the spin statistics connection we have just outlined provides just such a deeper motivation. Well, what about bosons? For bosons, putting R1 equal to R2, we see that psi for particle 1 at R1 and particle 2 at R1 is equal to psi for particle 2 at R1 and particle 1 at R1, which is an identity. There is thus no restriction on two or more bosons occupying the same quantum state. Thus, at extremely low temperatures, all the bosons in a system can condense into the lowest energy state, a phenomenon known as Bose-Einstein condensation, which was first predicted by Einstein in 1925. And in 2001, Cornell, Ketterle, and Beeman won the Nobel Prize for Physics for their experimental realization of Bose-Einstein condensation. So, boson wave functions are symmetric, as we have seen. That is, psi for particle 1 at R1 and particle 2 at R2 is equal to psi for particle 2 at R1 and particle 1 at R2, whereas fermion wave functions are antisymmetric. That is, psi for particle 1 at R1 and particle 2 at R2 is equal to minus psi for particle 2 at R1 and particle 1 at R2. What is the cause of this difference? The difference we now recognize is due to a new type of intrinsic angular momentum, which has the unfortunate name of spin angular momentum, from analogy with the Earth, which has an orbital angular momentum as it moves around the Sun, and it has a spin angular momentum as it rotates about its own axis. Okay, but this is just an analogy. Okay, so the bosons have integer spin. That is, the spin can take the spin quantum number s can take the values 0, 1, 2, etc. For instance, photons have spin s equal to 1, whereas fermions have half integer spin. That is, s can take the values half, 3 by 2, 5 by 2, etc. Electrons, for instance, have s equal to half. Thus, electrons have total spin angular momentum s equal to half. The z component of spin angular momentum, sz, can take the values of either plus half corresponding to upspin or minus half corresponding to downspin. Thus, the sz operator operating on psi gives ms the eigenvalue times psi, where ms can take the values plus or minus half. Thus, sz operating on upspin gives half upspin. The upspin is also represented as alpha spin. So, sz operating on alpha ket gives half alpha ket, and sz operating on downspin gives minus half downspin, or sz operating on beta ket gives minus half beta ket. The existence of this extra angular momentum was confirmed by German physicists Otto Stern and Walther Gerlach in 1922. What they did was they took a beam of s electrons from silver atoms. Note that s electrons have orbital angular momentum L equal to 0 and ml equal to 0. So they have zero orbital angular momentum, and they pass these electrons through a magnetic field. They observed a deflection in the magnetic field. Since the s electrons had zero orbital angular momentum, they should have gone straight and hit the screen in the middle. However, the electrons were deflected. Some of them were deflected up and hit the screen here, and some of them were deflected down and hit the screen here, which shows that the electrons possess an intrinsic angular momentum apart from their orbital angular momentum, and they can be of two types. The components Sx, Sy, and Sz of the spin angular momentum operator obey commutation relations similar to those for Lx, Ly, and Lz. Thus, commutator of Sx and Sy is equal to Isz in units of H cross, commutator of Sy and Sz is equal to Isx, and commutator of Sz and Sx is equal to Isy. Now we have Lz psi equal to ml psi. Similarly, Sz psi is equal to ms psi. In presence of a magnetic field, the initially degenerate levels for ms equal to plus minus half split, and the energy is given by this expression, where we see that this extent of splitting is proportional to the magnitude of the magnetic field B0. Okay, ms and g mu are constants. Okay, Now, if we impose an external radiation field of exactly this energy, that is the energy equal to the difference between the plus half and minus half levels, then the system can absorb the energy from the radiation field and make a transition from the lower energy level to the upper energy level. And this is known as electron paramagnetic resonance or electron spin resonance. So what exactly is electron spin? We have pointed out that the word spin is only an analogy. The concept of a spinning electron raises many conceptual difficulties. George Uhlenbeck and Samuel Goodschmidt proposed the concept of electron spin in 1926, but this is an unfortunate nomenclature because in a footnote they admitted that their proposal would actually lead to a velocity of the electron many times that of the speed of light. Okay. Pauli in 1927 was the first to propose a consistent non-relativistic theory of electron spin in terms of the Pauli matrices. So the spin angular momentum operator is related to the Pauli spin matrices, where the three Pauli spin matrices are given by sigma x equals 0, 1, 1, 0, sigma y equals 0 minus I 0, and sigma z equal to 1, 0, 0 minus 1 in terms of the basis skets alpha and beta for the upspin and downspin. Okay, and this is now known to be the non-relativistic limit of Dirac's 1928 relativistic theory of the electron. Note that the time-dependent Schrödinger equation shown here does not have a relativistically covariant form. The left-hand side is a second-order differential equation with respect to the space coordinates x, y, and z, whereas the right-hand side is a first-order differential equation with respect to the time. However, relativity requires that space and time have to be treated equivalently. The first to attempt a relativistically covariant theory of quantum mechanics were Klein and Gordon, and their equation is uniformly a second-order differential equation with respect to both the time coordinates and the space coordinates. The last term is the mass energy. Okay. Unfortunately, this equation has unphysical negative energy solutions. The spectrum is not bounded from below, and this means that the electron can keep on lowering its energy until it gets to minus infinity, and which means that an infinite amount of energy can be extracted from the system, which is obviously not possible. Okay. Dirac, on the other hand, proposed a first-order differential equation of the form h psi equals minus I alpha dot del plus beta m operating on psi equals I del psi by del t. Here alpha I and beta are anticommuting matrices with square equal to 1, that is the anticommutator of alpha I and alpha k, which is equal to alpha I alpha k plus alpha k alpha I equal to 0 for I not equal to k. Anticommutator of alpha I and beta, which is alpha I beta plus beta alpha I is equal to 0, and alpha I squared equals beta I squared equal to the identity matrix. Now if we let gamma 0 equal to beta, gamma I equal to beta times alpha I for I equal to 1, 2, and 3, and anticommutator of gamma mu and gamma nu is equal to 2g mu nu, then the Dirac equation becomes I gamma mu del mu minus m operating on psi equal to 0, where the convention is that repeated superscripts or subscripts should be summed over. The gamma and alpha are related to the Pauli matrices sigma, So gamma 0 equal to beta equal to I 0 0 minus I, alpha I equal to 0 sigma I 0, and gamma I is equal to 0 sigma I minus sigma I 0. The negative energy solutions are now associated with positrons, that is the electron's antiparticle with positive charge, while the positive energy solutions are associated with electrons. So there is now no possibility of a positive energy electron tunneling through the zero energy and becoming a negative energy positron. The positive energy and negative energy solutions correspond to different sets of particles. The predicted antiparticle, the positron, was discovered by Carl Anderson in 1932 while studying cosmic rays, and this represented a major success of Dirac's relativistic theory of the electron. We have discussed fermions and bosons. However, there is a third possibility which was actually not realized until the 1980s, and that is that psi for particle 1 at R1 and particle 2 at R2 can be equal to psi for particle 2 at R1 and particle 1 at R2 times e to the power I theta, a phase factor. Thus, these particles suffer a phase change upon particle interchange. If the phase angle theta is equal to 0 or 2n pi, where n is an integer, then the phase factor e to the power I theta is just 1 and the particles are bosons. But if the phase angle theta is equal to 2n plus 1 times pi, where n is an integer, then the phase factor e to the power I theta becomes equal to minus 1 and the particles are fermions. For any other value of theta, the particles obey neither Fermi-Dirac nor Bose-Einstein statistics, but they obey what is called fractional statistics, and they are called anyons. We now know that quasi-particles that consist of a charged particle and a magnetic flux tube, the composite of these behave as anyons. Thus, we have here an electron and a tube of magnetic flux passing through it, and the composite of these two behaves as an anyon. And that brings me to the second topic I want to discuss today, which is the quantum mechanics of the radiation field and the interaction of matter with the radiation field. Now, in classical electrodynamics, the energy of the radiation field is given by the integral of the electric field squared plus the magnetic field squared. Okay. So here d tau equals dx dy dz, E is the electric field, H is the magnetic field, and this can also be written in terms of the magnetic induction B and the electric displacement D. So the electric and magnetic fields satisfy Maxwell's equations, and in MKS units these take the form del dot E equal to rho, which is Coulomb's law, where rho is the charge density, del dot B equal to 0, which expresses the absence of free magnetic monopoles, del cross B minus del E by del T equal to J, which is Ampere's law, where J is the current density, and del cross E plus del B by del T equal to 0, which is Faraday's law. And the charge and current densities satisfy the continuity equation del dot J plus del rho by del T equal to 0. In classical electrodynamics, we introduce the scalar and vector potentials purely for mathematical convenience. Thus, the magnetic induction can be written as B equals del cross A, the curl of the vector potential A, and the electric field is given as E equals minus del phi minus del A by del T, that is the negative gradient of the scalar potential and the negative time derivative of the vector potential. And the scalar and vector potentials satisfy the wave equations Laplacian of phi minus del squared phi by del t squared equals minus rho, and Laplacian of A minus del squared A by del t squared equals minus j. The scalar and vector potentials are then invariant to arbitrary gauge transformations of the form A going to A plus gradient of lambda and phi going to phi minus the time derivative of lambda, where lambda is a scalar that satisfies Laplacian of lambda minus del squared lambda by del t squared equal to 0. For instance, we can choose the Coulomb gauge where the divergence of the vector potential is equal to 0, del dot A equal to 0. Now let us consider the interaction of matter with radiation. In presence of a radiation field, the canonical momentum becomes not just P, but P plus rho A, where rho is the charge density of matter and A is the vector potential of the radiation field, so that the total non-relativistic energy of matter in the presence of the radiation field is E equals integral 1 upon 2m P plus rho A whole squared plus rho phi d tau plus the energy of the radiation field. In 1959, Yakir Aharonov and David Bohm showed that despite the gauge invariance, the vector potential A has a fundamental significance in quantum electrodynamics that it does not have in classical electrodynamics. Consider electron beams passing on opposite sides of a tightly wound solenoid. So an electron beam is incident upon a beam splitter, which splits it into two beams, and the two beams pass on either side of a tightly wound solenoid and are then recombined in an interference region. The magnetic field is confined to the solenoid, and the electron beams never traverse any region with non-zero magnetic field. So there is no magnetic field in the regions traversed by either electron beam 1 or electron beam 2. Nevertheless, the vector potential is not zero in these regions. Aharonov and Bohm predicted a quantum interference effect when the two beams are recombined. In the Aharonov-Bohm effect, the electron beams passing on opposite sides of the solenoid produce a phase difference and thus interference when recombined. And this phase difference is proportional to the total magnetic flux through a closed loop around the solenoid, even though the electron beams never traverse any region with non-zero magnetic field. That is, the phase difference is given by the contour integral of A dot dx, which is equal to the magnetic flux phi. Okay? And this is because the vector potential A is non-zero along the two paths and is different along the two paths 1 and 2, and this gives rise to a non-zero contour integral of A dot dx and thus to interference. And the existence of this interference was experimentally confirmed by Chalmers in 1960. We shall stop here and continue next time with the implications of this for the molecular structure problem.